Next speaker is Tanya Bloch. Tanya is a PhD candidate in the Virtual Construction Lab at the Technion, which belongs to the Faculty of Civil and Environmental Engineering, and is housed in the National Building Research Institute. Tanya graduated from the Technion with a BSc in Civil Engineering, specializes in Structural Engineering in 2008, after which she served in the Construction Division of the Ministry of Defense, with Erez, which we saw before, as an Army officer for a number of years. She then completed her master's also here at the Technion in 2014 with a thesis on the subject of interior models and earthquake-damaged buildings for search and rescue. She already has 3 journal articles to her credit and is now working on her PhD research in the general area of application of AI with BIM to semantic enrichment code-checking application. The thesis topic is an evaluation of computational approaches for semantic enrichment of BIM models.
Okay. So good evening, everyone. Thank you for the introduction. I know you're all tired, so I'm going to be quick, I promise. As Guy said, I'm going to talk about the application of machine learning approach to semantic enrichment and to code checking as well. Sorry. So to begin with, we're going to try to understand this new term, semantic enrichment. And to do that, we're going to look at the information that we have in a BIM model. So naturally, we have the geometry of the elements that compose the model, but also we have a lot of this additional information about the properties of those elements, the functions of those elements, and their relationships as well. And all that information can be referred to as the semantics of a model. And there are actually 2 ways that all this information can be represented. So it could either be explicit, meaning that it's actually in the model file, it's stored in the model, but it could also be implicit, meaning that it's not really in the file, it's not in the model, but we can still somehow understand it. Just to give you an example of what I mean, so if we look at this layout of a standard apartment, it's not going to be hard for us to say that this is the bedroom. And if we look a little closer than the small space beneath it, we can say, okay, this is probably the bathroom. And since the 2 of them are connected, you can see a door there, then we can say, oh, then this is probably the master bedroom. Now, all this information is very important, but it's not really in the model. The space elements don't even have to be in the model. They don't have to exist in the model for us to understand all that. So this is implicit information. Now, thank you. Was that a clue for something? Just kidding, okay. Okay, now, theoretically, having all that rich information in a single model means that we should be able to reuse that information for other applications as well. And we have many applications for energy analysis, for structural analysis, and for code checking as well. But in practice, we know that it's not so easy to share information between the different tools. And then we do have what's called the problem of interoperability. And in addition to that, many of those applications, like code checking, they require very rich semantic information to be explicit in the model. So we can't just take the information we have in our design tool and put it into some other application. We have to somehow pre-process it and make it compatible to the application we want to use. So in other words, we have these 2 challenges. And actually, semantic enrichment offers the solution to both of those challenges, because if we look at the definition of what semantic enrichment is, it is a process in which domain expert knowledge is used to infer the semantics of a given model, to infer information that was not explicit in the model. And that information can be added to the model. And once it's added to the model, that means that it's readable to a computer, and we can actually access it, and then we can reuse it. So that's semantic enrichment. I'm going to try to give you just a general overview of the idea of our research. And to do that, we're going to look at this 2x2 matrix, because essentially, we have two tasks that we're interested in, which is the task of semantic enrichment and the task of code compliance checking. And we also already identified two approaches that can be applied to each of those tasks. So we have the, I'm going to say traditional, kind of traditional approach of logical rules, rule inferencing, but we also have the approach of machine learning. And the reason I have these two different colors here is because those two subjects that are highlighted in green are actually subjects that were explored before. So for instance, we have a research project called Seabridge that showed very good results for using rule inferencing for semantic enrichment. And for the code checking as well, we have existing applications that were mentioned here today before, like Solibri, like SmartReview, and several others as well. And they are based on rules. They're based on rule sets. But the other two cells you see here are actually subjects that were not explored yet. And they are the real interests of our research right now. So we're talking about the application of machine learning approach to semantic enrichment and to code compliance checking. And I'm going to show you a little bit of what we've done so far in terms of both of them. And I'm going to start with the semantic enrichment part, since it's actually my part of the research. So what we did, we defined a very small, maybe simple, but very important problem of semantic enrichment, which is the classification of room types in residential apartments. In other words, we want to be able to automatically identify which space in the model is the living room, which is the bedroom, which is the kitchen, and so on and so on. We did apply the rule inferencing approach on that as well, but as you can see, the result of this is that we could only classify 5 room types out of the possible 15. For the machine learning, any machine learning algorithm requires two things. It requires a data set, first of all, a set of examples of the objects that you want to classify. And it also requires you to identify the most informative features of those objects. But since we're talking about space elements, all space elements in the model are essentially boxes. And those boxes are very much alike. So there are actually very few geometric features that we could use that could really distinguish between the different room types. One feature that we did recognize is actually not about the geometry of those spaces, but about the connections between them. So for instance, if I know that this space is the kitchen right here, and I also know that in a standard apartment, usually I can't go straight from the kitchen to a bedroom, let's say, right? So I know that the space next to the kitchen is not going to be a bedroom. It could be a living room, could be a dining room, the entrance hall maybe, but it's not going to be a bedroom. So this is very informative, and we wanted to use that. And so what we did, we developed an iterative algorithm that is based on artificial neural networks, but what it does, it classifies a single space out of the whole apartment based on only geometric features, and then the connection features can be added, so the classification continues until you get all the spaces of the apartment. So unfortunately, I only had 150 examples. My data set was very small. And 70% of that was used to actually train the model. 30% was used for validation. And still, we got 82% accuracy on the validation set that was based on only geometric features. We also had additional 3 test cases, 3 apartments that we wanted to classify. And you can see an example here. And here we applied the iterative approach that I mentioned. The result of that is correct classification of all spaces in all 3 apartments. As for the code compliance checking, well, if we look, again, it's kind of the traditional process for code compliance checking. It consists of 4 parts. So we have the interpretation of rules, we have the pre-processing of the BIM model, and we have the rule execution in the report. But, and I already talked about the challenge of having to pre-process the model, and how semantic enrichment can offer a solution to that. But actually, the first stage of this, the interpretation of rules, is very challenging as well. And it is the subject of existing research that aim to translate the massive amount of codes of written texts into computer-readable rules. And that's very challenging, especially when you deal with performance-based codes. So we actually started thinking, well, what if we could do without this? Or could we have some kind of a automated checking routine that does not require compilation of rule sets? And we actually think we can, because if you look at any machine learning algorithm, it doesn't require rules, it requires examples. So theoretically, if we could have enough examples of models that are compliant to certain code, models that pass, and models that fail, we could kind of throw them all into some kind of machine learning algorithm. It doesn't matter right now which and what exactly it does, but it should be able, it should be able to learn from those examples and to generalize from those examples so that once we provide a new instance, a new model should be able to predict whether that new model passes or fails. So to test this, we wanted to check the compatibility or the compliance of apartment security rooms to the relevant code. And just for our guests, I'm going to say a quick note. Every standard Israeli apartment has to have a security room, which is a shelter. And also that it's a bit of a painful issue, the design of those shelters, because there are really lots of requirements. So this is a real and important issue for us. But the first challenge we had when we started this is that actually there are not many examples. There are not many models that contain those security rooms that we could use. And the models that we do have, that we can have, are actually models, it comes from the industry. And so the models that we can have are models that were actually checked before and fixed before, and they are compliant to the code. So we could probably have examples of models that pass, but we don't have any examples of models that fail. So we decided to create our own. So we used a random number generator to create 10,000 variations of a security room. And the way they were created is that 5,000 of them are compliant to a certain provision of a code. The rest of them are not. Overall, we used 16 conditions that we wanted to check against. So for a model to pass, it has to be compliant with all the 16 conditions. If a model fails, that means it's not compliant to either one or several of the conditions. The classifier that we used this time was decision trees. And again, 70% was used for training, 30% for validation. This time we got 99.9% accuracy on the validation side. We also created additional 20 cases to be test cases. Out of those cases, 2 were created so that they pass, and 18 fail. But this time, we restricted the number of issues for each failed case, which means that actually a failed case is compliant to 15 out of the 16 conditions. The result of this one was that we got correct classification of 18 out of the 20 cases. And we did get 2 false positives, but we really think that that's because we restricted the number of issues for each failed case. Conclusions. So I think probably the most important conclusion out of all of this is that machine learning is applicable to both semantic enrichment and to code compliance checking. And we already saw the benefits of using machine learning to certain problems of semantic enrichment that has certain characteristics. For the code compliance checking, we're really at the beginning of exploring this subject, but you saw the results, and that is very encouraging. So we do hope we'll be able to somehow ease this task of having to translate written codes into computer-readable rules. Promise I'll be fast, right?